Chapter 3. Ace the Reliability Pillar. Introduction. For a busy person who may not have time to go through the hundreds of pages of the well-architected framework, this guide serves as an abstract of the reliability pillar of the well-architected framework. Understanding the reliability pillar will ensure that you are equipped with the knowledge of the best practices in order to make your workload perform its intended function correctly and consistently when it is intended to. The reliability pillar. As AWS CTO Werner Vogel says, everything fails all the time. Your workload will also go through all sorts of tests, be in spike in load or failure of more than one component at a time. Due to this, it becomes important to keep reliability in mind when designing your architectures and evolving it over time. This paper provides in-depth, best practice guidance for implementing reliable workloads on AWS. As any pillar of the well-architected framework, the reliability pillar also covers the following two broad areas: design principles, definitions. Design principles. Following the various design principles highlighted in this pillar can help you achieve reliable workloads in the cloud. 1. Automatically recover from failure. You should identify key performance indicators as a measure of business value and monitor your workload against them so that an automatic action can be triggered when threshold is reached. 2. Test recovery procedures. Apart from testing your workloads for normal functionality, you should also test how they recover against failures. With the cloud, this can be made easy by automation to identify various failing components and making sure the recovery paths trigger in to maintain consistent outputs. 3. Scale horizontally to increase aggregate workload availability. Your heavily scaled-up resources can lead to too much dependency and, many times, may be a single point of failure. By scaling horizontally, your requests will be distributed across multiple smaller resources, thus making it a more resilient architecture. 4. Stop guessing capacity. In on-premises world, as the demand increases, the workload may not be able to sustain, leading to failure as there is very less scope of agile provisioning. With cloud-based workloads, you can easily monitor various metrics and set up scaling policy to add/remove capacity on demand without having to worry about the turbulent times of traffic spikes. 5. Manage change and automation. By making changes to your infrastructure through automation, you can track and review them. This also sets up operational procedures to automate infrastructure changes in the time of need. Definitions. AWS outlined 4 focus areas that encompass reliability in the cloud: foundations, workload architecture, change management, failure management. Let's go into the details of each of them to understand the best practices in these areas to achieve reliability in your cloud-based workloads. To achieve reliability, you must start with the foundations, an environment where service quotas and network topology accommodate the workload. These foundational requirements extend beyond a single workload or project and influence the overall reliability of the system. 1. Manage service quotas and constraints. Various service limits or quotas exist in the cloud to prevent accidental provisioning of more resources than you need and to limit requests rate to API operations so as to protect services from abuse. Also, physical resource constraints such as maximum available bandwidth on a fiber link and storage space on a physical hard drive exist. As such, this is a very crucial foundational requirement to be aware of such limits. Aware of service quotas and constraints. Various service limits such as EC2, EBS, and EIPs and VPC quotas exist in the AWS cloud, and you should be aware of such limits by referring to service quotas. Using this service, You can manage up to 100 service limits from a single location. Additionally, Trusted Advisor Checks includes your service quota usage to take necessary action. Manage quotas across accounts and regions. With environments spread across multiple accounts, you need to keep track of service quotas across all the accounts, since service limits are set on per account and in most cases per region basis as well. Using AWS organizations, you can automate updating the service limits of newly created accounts with the help of predefined template to maintain a uniform structure across the organization. Accommodate fixed service quotas and constraints through architecture. Some of the limits, such as network bandwidth over your DX connection or AWS Lambda payload size, are fixed. Your architecture should be designed considering these unchangeable service quotas and physical resource limits. Monitor and manage quotas. You can monitor your utilization and keep track of threshold breaches by setting up appropriate CloudWatch alarms based on the service quota metrics for the corresponding services. Automate quota management. You can also integrate your change management or ticketing system with service quotas to generate limit increase requests automatically based on the threshold breaches. Ensure that a sufficient gap exists between the current quotas and the maximum usage to accommodate failover. Your failed resources are also considered against your quota until they are terminated. Considering this, you should consider at least an AZ-level failure of resources to calculate the gap. 2. Plan your network topology. While architecture for highly reliable environments, you should plan for intrasystem and intersystem connectivity between various networks, public and private IP management, and DNS resolution. Use highly available network connectivity for your workload public endpoints. For your workload, which is publicly accessible, you need to use a highly available routing. Services such as Route 53 for DNS, Amazon CloudFront for CDNs, AWS Global Accelerator for Anycast routing, and ELB for HTTP or TCP termination can help you get a managed and highly available endpoint for your end-user connectivity. You should also plan for mitigation of external attacks, as public endpoints are at more risk of exposure than any other resource. AWS Shield can provide you automatic protection against these kinds of attacks and allow only legitimate traffic to pass through. Provision redundant connectivity between private networks in the cloud and on-premises environments. For private connectivity to your on-prem network, which relies on services such as Direct Connect via physical fiber or AWS VPN via secure tunnel over the Internet, you need to plan for failure by provisioning appropriate redundancy. For Direct Connect connections, you should plan for router, fiber, provider, and POP-level failure by selecting redundant paths. If cost is a constraint, then you can plan for a secondary VPN connection as a backup of your primary Direct Connect connectivity. However, you should be aware of the difference in performance over the two channels. Ensure IP subnet allocation accounts for expansion and availability. Your VPC CIDR range and subnet size cannot be changed once created, so you need to plan in advance to allocate enough IP block to accommodate your workload requirements. Additionally, you need to leave some room for future expansion by keeping unused space in each subnet. Prefer hub-and-spoke topologies over many-to-many mesh. If you have only two different networks, then you can simply connect them using one-to-one channel, such as VPC peering, DX, or AWS VPN. But as the number of networks grows, the complexity of meshed connections between all of them becomes untenable. AWS Transit Gateway can help you maintain a hub-and-spoke model, allowing you to route traffic across your multiple networks. Enforce non-overlapping private IP address ranges in all private address spaces where they are connected. You cannot natively connect two VPCs or your VPC and on-prem network if they have overlapping IP address ranges. In order to avoid such IP conflicts, you should use IP address management, IPAM, systems to manage allocating of IP address ranges for various resources. Workload architecture. You need to make upfront design decisions to create a reliable workload. This includes both software and infrastructure components. Following patterns can be referred to for reliability. 1. Design your workload service architecture. Build highly scalable and reliable workloads using a service-oriented architecture, SOA, or a microservices architecture. Service-oriented architecture, SOA, is the practice of making software components reusable via service interfaces. Microservices architecture goes further to make components smaller and simpler. Choose how to segment your workload. You should avoid monolithic architectures wherever possible. Instead, you should either choose between service-oriented architectures, SOA, or microservices. With the shared release pipelines, rigid scaling, a high impact of changes, monolithic architectures make it hard to adopt new technologies. With the smaller segmentation offered by SOA or microservices, you get greater agility, organizational flexibility, and scalability. Build services focused on specific business domains and functionality. Your services build using SOA and microservices should have a very specific task to do. This helps you understand the reliability requirements of different components. A domain-driven design (DDD) model can be used in microservices to model business problems using entities. For example, in a dating app, the entities can be user sign-up, verification, login, profile management, matches, and payments can be different entities. Then you can further identify the entities which share common features to group them using bounded context. In this case, it would be the sign-up, verification, and login as a part of a bounded context. Using this context, you can then identify the boundary of the resulting microservices architecture. Provide service contracts per API. Each service created using microservices can be exposed using an API which has a very specific task to accomplish. Various teams in your organization can make use of this API and agree upon a set of expectations such as rate limits, performance, and API definitions. With such a contract in place, owing team can configure their API to meet this requirement so that the overall workload outcomes are consistent. 2. Design interactions in a distributed system to prevent failures. Distributed systems rely on communications networks to interconnect components, such as servers or services. Your workload must operate reliably despite data loss or latency in these networks. Components of the distributed system must operate in a way that does not negatively impact other components or the workload. Identify which kind of distributed system is required. There are two main kinds of distributed systems. 1. Hard, real-time distributed systems, which require responses to be provided as soon as the request is received. Even though the requests can be unpredictable, your system should be able to respond to it rapidly. 2. Soft, real-time distributed system, which have a more generous time window of minutes or more for response. Based on the business requirements, your workload should be choosing the system and accordingly set up the reliability metrics for that. Implement loosely coupled dependencies. Loosely coupled architectures help isolate behavior of a component from other components that depend on it, increasing resiliency and agility. On the other hand, in tightly coupled architectures, changes to a component force other components that rely on it to change as well. For example, if your client directly communicates with an EC2 instance, then the failure on the EC2 directly impacts the client as it behaves as a tightly coupled synchronous environment. By using a load balancer to send requests to various EC2 instances, A failure on a single EC2 instance will not affect your client. Similarly, asynchronous workflows with the help of Amazon SQS will enable your independent worker nodes to process messages in case of failure of one of them. Make all responses idempotent. Each request received by your service should be served exactly once. So if you have multiple requests which have the same effect, then it is possible that they can be erroneously processed multiple times. By using idempotency tokens in your APIs, you can guarantee that even if your service receives a request more than once, it is not going to create duplicate records or errors. Do constant work. Sudden large or rapid changes in your systems can lead to your service getting overwhelmed. Instead, it should be designed to interact in the same as it would in case of a large failure. This should be specially applicable for health check systems, and they should constantly work with the same payload, even if no server is failing or all are failing. 3. Design interactions in a distributed system to mitigate or withstand failures. While the advantages of having a distributed system far outweigh its challenge, your reliable system should be designed considering the failures which can occur in the distributed systems. One of the most common is the communication between different systems. Your workload should continue to operate reliably despite data loss or latency between the network. A few best practices to prevent such failures are: implement graceful degradation to transform applicable hard dependencies into soft dependencies. When multiple systems are dependent on each other and one of them fails, instead of cascading failures across all components, the immediate system connected to the failed system should be able to provide a fixed response in order to avoid passing the failure to other dependent components. Throttle requests. Your system should be designed to know the capacity which they can serve requests, and higher rate of requests should be throttled by rejecting them and sending a response indicating that throttling has occurred. This indicates the client to back off and try with a slower rate instead of constantly pushing your system to process requests above its capacity. Services such as API Gateway have methods to throttle requests, and similarly, Amazon SQS and Kinesis can buffer requests as well. Control and limit retry calls. In case of failures, your client should not just constantly retry, but delay the requests with progressively longer intervals. This is known as exponential backoff, which increases the interval between subsequent retries. Fail fast and limit queues. For server side of things, if your workload is unable to respond quickly, then you should fast fail instead of keeping the resources reserved. Similarly, for high number of requests, the requests should be buffered, but the queue size should not be too long, which may result in stale requests which the client has already timed out. Set client timeouts. Your client-side timeouts should be determined after verifying the end-to-end structure, and you should not rely on the default values, which in some cases can be too high. This avoids unnecessary retries, thereby avoiding system overload. Make services stateless where possible. Your services should not store state in memory or in the local disk. This enabled client requests to be sent to any compute server without dependency on an existing one in case of failure. For example, you may have a web service that serves traffic behind a load balancer, and your initial client session is established with web server 1, which also maintains the session state. In this case, if the web server 1 goes down, the web server 2 will not have any information about the client state. In such situations, the session state should be offloaded and maintained in services such as Elasticache. For serverless architectures, this can be done using DynamoDB. Implement emergency levers. Emergency levers can be used to mitigate the availability impact on your workload. This can be as simple as serving static response or blocking a specific type of traffic entirely. This ensures that the entire workload availability is not affected, and you can focus on determining the root cause of the issue affecting availability. Change management. Your workload should be designed to adapt to changes, which can be either due to a spike in demand or feature deployments. Here are the best practices for change management. 1. Monitor workload resources. Monitoring your workload enables it to recognize when low performance thresholds are crossed or failures occur, so that it can recover automatically in response. There are 4 distinct phases in monitoring. Generation. You should monitor all the components of your workload, which may be using AWS services or customer services. While AWS services can be monitored using CloudWatch metrics, your custom workloads can be monitored using third-party tools to either integrate with CloudWatch or use their custom solution. Aggregation. Similar to metrics, logs from all the components should be stored either in CloudWatch or S3, and then define metrics based on specific filtered applied to the logs. For example, in a web server logs, you can apply filter to monitor HTTP 5XX error, which may not be determined using predefined metrics. Real-time processing and alarming. Your metrics should be processed in real time by first notifying appropriate subscribers by using Simple Notification Service, SNS. These subscribers can either be your operations team or other AWS services to take appropriate action. The actions taken against the breach of a metric threshold should be automated in nature by triggering auto-scaling events or implementing custom logic using Lambda functions. Storage and analytics. Apart from defining custom metrics from your log data, you should also analyze the log files for broader trends and getting insights into your workload. Amazon CloudWatch Logs Insights comes with both predefined queries and ability to create custom queries to determine trends your workload. All the above phases should be reviewed periodically to implement changes as the business priorities change. You can use additional auditing mechanisms using CloudTrail and AWS Config to identify when and who invoked an AWS API or made an infrastructure change. 2. Design your workload to adapt to changes in demand. Your workload should provide elasticity so that it can scale in order to meet the demand at any given point in time. Use automation when obtaining or scaling resources. For your EC2 resources, you can use auto-scaling to scale out or in according to demand and trigger these actions by monitoring specific workload metrics. Usually with the Amazon managed services such as S3 or Lambda, the scaling activities can be taken care by service itself, and it automatically scales up to meet the demand. Configure and use Amazon CloudFront or a trusted content delivery network. Your content delivery network services, such as CloudFront, can serve static content to your end users and which not only reduces load on your computer resources, but also provides an optimal experience to the clients. Obtain resources upon detection of impairment to a workload. Instead of just monitoring your resources metrics, you should monitor the overall workload metric to detect failures by using health checks. These resources should be reactively scaled by using automatic or manual mechanisms. Obtain resources upon detection that more resources are needed for a workload. You should configure the scaling criteria based on workload-specific parameters such as request rate, time to process each request, and request/response size. Based on these parameters, your scaling criteria should be decided and also modified if there is a change in parameters. Load test your workload. You should implement a load testing strategy to determine if the scaling activities can keep up with the demand. With the cloud, it is easy to create new resources and terminate them after the testing is done. So the cost of testing is a fraction of what you would usually pay in the on-premises environment. 3. Implement change. Use runbooks for standard activities such as deployment. By using runbook for standard changes, you can be aware of the next step to be taken in case something goes wrong. These runbooks can be created for both manual and automatic changes and reduce ambiguity in your change management process. Integrate functional testing as part of your deployment. Your functional tests should be one of the most important tests as a part of deployment. These should be done in pre-prod as well as prod environment, and any failure should result in rollback of the changes. Integrate resiliency testing as part of your deployment. Your deployments should include resiliency tests in order to ensure that your workload continues to function in case of failure of a component. Deploy using immutable infrastructure. Your code changes or updates should not be deployed directly to the production systems. Instead, you should spin up new resources to implement these changes and move the traffic to the new resource. The shift of traffic can be done either using canary deployment, where a small number of customers are directed to the new version, or by using blue/green deployment, where a full fleet of application is deployed in parallel and a percentage of customers are directed to the new group of resource. Deploy changes with automation. You should make use of automation by implementing CI/CD pipelines through AWS Code Deploy, which automatically deploy application code to EC2, Lambda, ECS, and on-premises network. This ensures a consistent approach every time you want to deploy changes to your workload. Failure management. Your workload should be able to withstand failures at any level. This can be done by using the following strategies. 1. Back up data. Identify and back up all data that needs to be backed up, or reproduce the data from sources. You should identify all sources of data which, if lost, can affect your workload outcomes. This data, in turn, should be backed up depending on the resource. Amazon S3 can be one of the most versatile backup destinations, and part inbuilt backup capabilities in services such as EBS, RDS, or DynamoDB. Secure and encrypt backup. Access to the backup of your data should be secure in the same way you would do to the original data. You can use IAM to restrict access to the backup data and also encrypt it using AWS KMS. Perform data backup automatically. You should determine a backup schedule and run the backup process automatically. AWS Backup Service can provide you a centralized view of all your backup schedules across multiple AWS services. Perform periodic recovery of the data to verify backup integrity and processes. Your backup should meet the recovery time objective and recovery point objective, and this should be tested by performing a recovery test. You can set up a test environment in which you can restore backup data and test for its integrity and content to meet your goals. 2. Use fault isolation to protect your workload. By setting up fault-isolated boundaries, you can limit the effect of a failure to a limited number of workloads. A few best practices around this are: deploy the workload to multiple locations. Your workload should be employed across multiple locations, and this should start with spreading the components in different availability zones within an AWS region. This ensures that even if there are component-related or AWS AZ-related failures in a specific availability load, you can continue to serve the traffic using the other AZs. If there are extreme availability requirements or other business goals, then you can also follow a multi-region architecture. Additional locations where you can deploy your workload are AWS local zones, edge locations such as CloudFront or Global Accelerator, and even the on-premises network. Automate recovery for components constrained to a single location. If there are workloads which are restricted to running a single availability zone or on-premises network, then you should implement automatic recovery either by provisioning redundant components or using backup solutions. This is specifically application for high-performance compute (HPC) workloads or with services such as Amazon EMR or Redshift. Use bulkhead architectures to limit scope of impact. Bulkheads in ship are the partitions to divide the ship into different compartments so that even if one part was damaged, the rest remained intact. Similar practice and be used by implementing data partition or using cells for your services. Your customer requests should be routed to different cells based on shuffle sharding, which ensures that only a limited number of customers are impacted in case of an event. 3. Design your workload to withstand component failures. Your workloads should be architected for resiliency, and they should be able to continue running in case of component failures. Some of the ways in which you can achieve this are: monitor all components of the workload to detect failures. You should monitor both technical failures of workload components as well as business metrics from running the workload that gives you an overall status of how your workload is helping in achieving the business outcomes. Failover to healthy resources. By using health check mechanism in elastic load balancing or Route 53, you can monitor the health of the workload in specific location and fail over to the healthy resources by the means of load balancing changes or DNS record update. Automate healing on all layers. The ability to restart is an important recovery mechanism, and it is application at all layers of your workload. For simple component failures, by making the services stateless, you can replace the entire component, such as EC2, as a part of restart. For large-scale replacements, such as availability zone failures, it is generally better to preferred an alternate availability zone as preferred one till stability is achieved, instead of provisioning multiple resources at once in the impacted AZ. Send notifications when events impact availability. Even if an issue caused by an event is automatically resolved, you should configure notifications to identify underlying problems that need to be investigated and avoid reoccurrence. 4. Test reliability. Use playbooks to investigate failures. Perform post-incident analysis. You should review any customer-impacting events to identify the contributing factors and make changes to take preventive actions for the future. You can also add any additional tests to catch failures before they occur in real time based on the findings from the analysis. Test functional requirements. By running synthetic testing such as canary testing, you can simulate the customer experience and understand if the workload meets its functional requirements. CloudWatch Synthetics can help you create canaries to monitor your customer-facing endpoints and APIs to monitor these. Test scaling and performance requirements. In the cloud, you can provision and terminate production-scale test environments and run load tests to ensure that they scale up to meet the performance outcomes with demand. Before load testing, you need to make sure that your scaling settings, service quotas, and base resources are configured to run as expected under load. Test resiliency using chaos engineering. Chaos engineering is a way to inject failures into your pre-production and production environments. There are many open-source tools such as Netflix Chaos Monkey, which can help you inject failures and understand how your workload reacts to different failures. Conduct game days regularly. Using game days, you can exercise your procedures for responding to events and failures as close to production as possible. These will help you understand where improvements can be made and give your organization an experience to deal with production-impacting events. 5. Plan for disaster recovery, DR. Based on your business needs, you should implement a disaster recovery strategy based on the locations and function of your workload and data. Some of the key things to keep in mind are: define recovery objectives for downtime and data loss. Your workload should have a recovery time objective, RTO, and recovery point objective, RPO. You should identify the RTO to set the maximum acceptable delay between interruption of service and the restoration of service. The RPO should be defined considering the maximum amount of time since the last data recovery point. Use defined recovery strategies to meet the recovery objectives. Based on your RTO and RPO, you can use one of the following strategies which have different complexities and order of RTO/RPO. A. Backup and restore, RPO in hours and RTO in 24 hours or less. You can back up your data and applications using point-in-time backups in a DR region and restore it to recover from disaster. B. Pilot light, RPO in minutes and RTO in hours. You can actively replicate your data and workload architecture to a DR region. In this case, while your data is most up-to-date, the resource will be switched off and only started when the DR failure is invoked. C. Warm standby, RPO in seconds and RTO in minutes. You can have a fully functional version of your workload running in a DR region, which includes both active components as well as data. However, the components will be running a scaled-down version to minimize the cost of running the workload. D. Multi-region active/active, RPO near zero and RPO potentially zero. In this case, you can have same copies of your workload running in two different regions, same as what you would do in different availability zones within a region. Since the workload is up to date across different regions, you have the minimum downtime in case of failure of a particular region. Test disaster recovery implementation to validate the implementation. Your DR strategy should be tested to ensure it continues to achieve the business outcomes based on different recovery paths. These recovery paths can be used to test the scaling, latest data availability, and overall architectural functionality in the DR site. Manage configuration drift at the DR site or region. You should ensure that the infrastructure, data, and configuration as needed in DR site or region. This includes having the latest copies of AMIs and service quotes, as you would have in the active region. Automate recovery. Based on health checks, monitoring business metrics, and third-party tools, you can automate the system recovery and route traffic to DR site or region. Review based on cost optimization pillar. Some of the questions which you will be going through when you review your workload against the reliability pillar of the well-architected framework are: REL1, how do you manage service quotas and constraints? REL2, how do you plan your network topology? REL3, how do you design your workload service architecture? REL4, how do you design interactions in a distributed system to prevent failures? REL5, how do you design interactions in a distributed system to mitigate or withstand failures? REL6, how do you monitor workload resources? REL7, how do you design your workload to adapt to changes in demand? REL8, how do you implement change? REL9, how do you back up data? REL10, how do you use fault isolation to protect your workload? REL11, how do you design your workload to withstand component failures? REL12, how do you test reliability? REL13, how do you plan for disaster recovery? DR. The answers to these questions during the review help you identify any gaps in your existing workloads and implement the best practices in your AWS environment.